Have you ever wondered how computers can evolve solutions just like living things evolve in nature? That's exactly what happens in a genetic algorithm, a technique inspired by Charles Darwin's theory of natural selection. Instead of evolving animals or plants, we evolve solutions to problems. And at the core of this process are three key steps: selection, crossover, and mutation. Let's explore how these three steps help machines learn and improve generation after generation. First, let's start with selection. Imagine we have a population of possible solutions, just like a population of animals. Each solution is like a creature, and its fitness represents how good that solution is. For example, if we're using a genetic algorithm to design the most efficient car, then the fitness might represent how fast or fuel efficient that design is. In the selection stage, we evaluate every individual in the population using a fitness function. Then, we pick the best performing ones, or sometimes a random mix weighted by their fitness, to act as parents for the next generation. There are many selection methods, like roulette wheel selection, where solutions with higher fitness have a greater chance of being chosen, or tournament selection, where a few random solutions compete and the best one wins. The main idea is simple. Good solutions get a higher chance to reproduce and pass on their traits to future generations, just like natural evolution. Now comes the second step, crossover. This is where things get really interesting. Crossover is like genetic mixing. It takes two parent solutions and combines parts of each to produce new offspring. Think of it like combining traits from both parents. If one parent represents speed and the other represents efficiency, their child might inherit a bit of both, maybe fast and efficient. In technical terms, crossover can be done in many ways. In single-point crossover, we split both parents at a random point and swap parts. In two-point crossover, two cut points are used to create more variety. There's also uniform crossover, where each gene is randomly chosen from one of the parents. Crossover helps explore new combinations of features, and sometimes it produces better solutions than either parent. It's nature's way of saying, let's mix and match to see what works best. Finally, we have mutation, the last but crucial step. After crossover creates offspring, mutation slightly alters some of their genes randomly. For example, if a solution is represented as a string of numbers or bits, mutation might flip a bit or change a value. Why do we need mutation? Because without it, the algorithm might get stuck. All individuals could start to look too similar, and we might miss better solutions. Mutation adds diversity and allows the algorithm to explore new areas of the search space that crossover alone might not reach. Just like in real life, small random mutations sometimes lead to big evolutionary improvements. So to recap, selection chooses the best solutions, crossover combines their strengths, and mutation introduces creative variations. Together, these three steps allow genetic algorithms to evolve solutions over many generations, getting closer and closer to the best possible answer. That's the beauty of evolution. Whether in nature or in code, the fittest always survive, improve, and adapt.